Okay, cool. So, yeah, like I was just saying, is that this next section we're going to talk a lot about the mathematics, linear algebra in particular, and using that with NumPy. And so, kind of starting off like what linear algebra is. First of all, who's had experience in linear algebra? Give me just a kind of quick thumbs up. Yeah. So maybe some. So, Asan, yeah.
Um, yeah, I'll say no for now.
Okay, so maybe a little bit at some point, but practically no. Yeah, that happens. Yeah, depending on your familiarity, linear algebra can be like, oh yes, I know linear algebra, or it can be like, oh, it's been a long time since I've done this, and it's okay. But basically, you can think of like almost everything that we're going to do, including more of the advanced machine learning models, like what's it called, neural networks and stuff like that, with deep learning. It's all based around linear algebra. Um, and so it's basically what is linear algebra? It's the study of vector spaces. And essentially it's just a space that you can span with a vector. So if you remember back, whenever you learned about vectors, they're essentially, I think of them like, I always see them as arrows, but basically it's just like saying, oh, direction. Like that's kind of the general idea of how we interpret vectors as like a physical thing. But vectors can mean for a lot of different things. We actually, each feature you guys did for your project is a vector. Like that is kind of like it's spanning out a vector space, or yeah, vector space. And of course, it's called linear algebra because things are linear. Math makes sense, at least somewhat, right? So linear relationships, there are of course other types of algebra, if you didn't know, but we're not going to talk about that right now because we're just talking about linear algebra, and that's the majority of what you'll do. You probably heard a lot of these terms. For example, we use vectors, matrices, you might have heard scalars. I might have also heard more recently in just people's vocabulary is tensors. And tensors we'll find are basically just a general vector matrix kind of object. It's a way kind of organizing things, and we'll talk about what that is. And then we're going to be talking about some, eventually, mapping and dimensionality. This is why we would use linear algebra. And basically, it allows us to kind of do things where things are very related to each other. We can basically reduce the dimensions so we don't have to worry as many features. So if we had like 20 features, but a lot of these features are basically correlated with each other, we can use something called PCA to reduce that dimensionality. Okay. And then again, I said use a lot for machine learning. So you can kind of think like linear algebra can be used for like a lot of different things, like the formalism. So like I said, all your features that you guys did in your project, which was like number of bedrooms, square footage, those are all, what's it called? They can be described in linear algebra. In fact, if you think about it, whenever you have those series in pandas, that is like a vector essentially, and we'll see that relationship. But also you can take other information, especially like, for example, images and pixels. So for example, in certain algorithms, particularly convolutional neural networks, will use linear algebra to basically take a picture and essentially make it into like vectors, into like a matrix of like, or I should say really a tensor of information. And we can pass that through using linear algebra to figure out information about what's in that picture. And then same thing for language. We'll actually make vectors from words and stuff like that. This is called NLP, natural language processing. It's one of the big areas of topics right now. It's pretty exciting. So anyway, that's why we're going to learn linear algebra. It's not just for fun, though I guess you could learn it for fun if you want. All right, so we'll get right into it, is that we have different tensors. And like I mentioned, there's scalars, vectors, matrices. It's really about dimension. So like scalars, vectors, matrices, and then into tensors, they're all the same, like they're all very related. It's just all about what, how do I say this? What dimension they are. So we'll kind of look at it a little bit. Oh, of course I didn't upload this video, but anyway, actually I think I have it in here. So this is from the module, I stole it directly from the curriculum, so we can see a little bit better. But while that loads, of course, learn takes a while. Just to see what a difference between a scalar, a vector, and a matrix. So we can see here's a scalar, a vector, a matrix, and then a tensor. So you can see that they're actually very similar. They're holding usually, in this case, we usually talk about linear algebra being numbers and stuff like that. But they could be like floats, it can be integers. So you can see it's going to be you're going to see a very close similarity with what we've been doing with pandas. And that's because we've been using NumPy within pandas. But we have a scalar here, which is a single one, usually, well, okay, I'll talk about it in a second. Then we have a vector with these parts right here. We have a matrix with multiple, and you can kind of see this tensor right here. It's kind of like, this bracket within a bracket kind of deal. And so We can actually talk about dimensions. So anyone got an idea what dimension a scalar is? Take a wild guess. I see Matt making this from 0, right? Scalar is a 0 dimension. And basically a scalar is just a number. That's all we really talk about when we're talking about a scalar. And then going into like vectors, for example, a vector is, anyone got a next guess what the next dimension is? Yes, on 1. All right, yeah, it sounds like we're just counting, right? And of course the matrix, anyone got a guess? Was it 5? you were so close. Yeah, I know. You're just joking. Yeah, too. It's funny when I'm showing like my wife my videos once, and she's like, "It sounds like you're playing Blue's Clues with them sometimes, like you're talking to the screen as you guys are silent." But anyway, yes, you're right. So it goes like basically up in dimension, and then we can see this tensor in particular is the dimension 3. In fact, tensor is a much more common word, but I've used to learn it as what's it called, a 3-dimensional or 3D matrix. But really it's more accurate to say they are in fact a tensor. And then we can actually go into 4D, 5D. I mean, it can go however high you want. So that's where we just call everything a tensor after that point. There's no reason to call something particular a 20D something special name. But you'll mostly deal with vectors and matrices when you're dealing with linear algebra, probably 3D matrices when we're talking about it to demonstrate it, but just know that most of your data is going to be multi-dimensional, like in higher dimensions. I think the last one we just had was 5 dimensions. So let me make sure I run this. So we can start looking at how we can create these in NumPy. And note that you'll see me create them in different ways. And so we'll kind of talk about this. So right here, I put S as a scalar. We can basically use NP arrange. Okay, so you can think of it as like a range of 1. And I can display that S. And you can see right here is that it's just going to be a single number. It's an array of 0. Note that the difference between display and print, they do the same information. Display is actually, if you're curious, so you can see when I display it like this, when I type an S at the bottom of a cell and I run this, it actually calls the display function explicitly. If I put print, you'll notice that print actually looks a little bit different from display. You'll see that it'll display it like this. So sometimes I'll call print just to kind of show you so I don't have this array, but this is giving us information that is a NumPy array. That way it knows, hey, this is not just a normal list, this is a NumPy array. But print will, the way it prints out is basically just looks very close to a list without the commas. Okay, but you can see our scalar usually is just a number. Sometimes we'll put it inside within the brackets just so it's clear that we're talking about a scalar, not just a random number. Okay, a vector is a 1-dimensional. We can see right here NP arrange, and this is a quick way to write what's it called? Basically getting a range from 0 to 4. In this case, it'll be 4 different elements. And we can we'll display that part. And then we can also do this linear space, which I'll show you in a second. But you can see right here is that when I display this, you can see there's my array or my vector right here. You'll notice that sometimes by default that it'll go to horizontal like this. You can create a vector, which is more like this. It technically writes it as a 2D kind of shape, but we'll see how that's very similar to this horizontal. But this is important because depending on how our array, really our vector or matrix is set up, we'll see we can do certain math on it. So we have to make sure it's in the right format. So something to pay attention, especially with vectors, you'll have to do something called transpose. We'll get into that. But linear space, like I was mentioning, it's kind of a neat trick. For example, this basically is built into NumPy. And this allows us to span out from a value to another value. So in this case, we're using NumPy to get the pi value, 3.14, you know, forever and forever. So negative pi to positive pi, and we're going to split it along 10 points. So if you look at this now, when you display this, it'll start with negative pi, or approximately negative pi, and it'll go over through 10 elements all the way to positive pi. I could have easily also done like, let's say 5 to like 0, and you can see that's the same thing as going out all the way over here. Note that you can do a lot of different little things on here, but this is going to be useful, especially when you're plotting. You can create these kind of arrays very quickly. So if you want to go, oh, I want to go from 0 to, you know, 10 or 100 or whatever value you want, min, maximum, you can quickly create this to have your inputs, kind of like your tick marks along your graph. So that's a useful thing. Then we have our matrix. So you'll notice me use this kind of notation, which I think is super useful, is I'm making a range here because this will just create a range. So if I actually get rid of this part, you can actually see when I do NP arrange, it's just 1D, right? It looks like a vector. But if I don't want a vector, I want a matrix in this case, right? So I can actually use something called dot reshape, which will take an array from a NumPy array, I should say, and we'll reshape it to this dimensional set, okay? Or I shouldn't say dimension. Well, it basically creates it into this, what we call shape. So in this case, I'm actually reshaping it into, I'm reshaping this into 4, 2. And so we'll see now, if I run this, you'll see that there are 4 rows and 2 columns. So, and again, if I did print, it's a little easier because we don't have that array in there. But you can see that's very close to what we saw over here when we have a matrix, where we have like 2 columns and 2 rows and 2 columns, versus here we have 4 rows, 2 columns. And note that I just put this multiplied here just because it's easier for me to like visualize quickly to this. Basically, the number of elements on the reshaping have to match what's already in this range in here, or sorry, this array. If I did 4, 1 like this, you'll see that it'll give me an error. It says, hey, I can't do that. But if I did, let's say 4, 2, which is 8, and then I multiply by 2 again, you'll see it also doesn't work. So you just have to make sure the shape matters and stuff like that. So that's why it's going on here, And that's why it's a little easier sometimes when you're creating these from scratch and you're just making a range. You can do something like this and then do a reshape like that. Also note that reshape takes in a tuple. It's not 4, 2. It's a tuple of 4, 2. That's important. Reshape technically only takes in one, in this case, 1 parameter. So if you put in 4, 2, like we can see those errors. So these are like, I'm kind of showing you some stuff that will come up if you accidentally put the wrong thing in there, what happens. In this case, it actually works through here, but you have to be kind of careful about how you pass that in, right? So just be aware. I would check out the documentation because there's some extra stuff you can do with reshape. But these are usually the ones I see when we start dealing with, especially neural networks, people will reshape it in the wrong place. So keep an eye on that. Okay. And then we have a 3D tensor, which of course tensors are just a general object. But you can see here I have 3D, so we have, it's going to be 4, 2, 3. So I did reshape that 4, 2, 3. And you can see here, I have, 4 of these guys. You can think of them like as 4 matrices. 2 rows, and then 3 columns. Okay. So any questions on this?
You have 3 numbers in that tuple there. Are you allowed to do that?
Oh yeah, so this is a Python thing. So you can, tuples, even though it should sound like 2, right? A tuple just means like this structure. It's essentially like a list. So for example, if I have, let me make a new cell just to hammer this in. So like if I have A equals 1, 2, 3, 4, 5, right? That's obviously my A, right? I could also rebroadcast it as a tuple, right? So you can see here is that it is a tuple like this. Okay. But yeah, so tuples, what's it called? Tuples are like essentially like immutable list. Like, so lists, we can actually change those parts. A tuple basically is like I call it something. This is a thing. But yeah, you can have any number, including just 1 in a tuple. So you can see right here, this is how it shows that even though there's only 1 element in here, it's showing, hey, this is in fact a tuple. So you'll see this kind of notation with this comma. And basically that's the way to print out. So you know when you print it out, it's like, oh, that's just not just a number or just a number with parentheses. It's like, oh, this is in fact a tuple. Cool. Good question though. Yeah. So anyway, yeah, you can see this reshaping and stuff like this. And we'll talk a little bit about what this is. But one way I kind of look at this is that as we go up in higher and higher dimensions, you can kind of think of like things are being built out of each other. So for example, I have a scalar. A scalar is just like a single number, right? A vector is basically a bunch of scalars, okay? And this is really obvious when we, I'm just gonna show you guys this real quick, reshape. Oh, yeah, so you can see sometimes you'll see vectors like this, and that makes it really obvious that this is essentially a bunch of scalars. You kind of see that kind of aspect, right? Just like this one. And then you can think of a matrix as a bunch of vectors. So you can think of like almost like a list of vectors now. And so a 3D tensor, right, 3-dimensional tensor, is a essentially a list, array of matrices. So this is a matrix right here. This is a matrix right here. This is the matrix right here. This is the matrix right here. So you can see there's 4 matrices, and each of those matrices, there's 2 vectors like this. And then within each of those vectors, there are 3 scalars, 3 elements. Cool. All right, that's the way I think of it, and I think that's useful, especially to get in higher and higher dimensions, being like, wait, what's a 5th dimensional tensor? And you have to think, oh, it's a 5th dimensional tensor. Each element in there is a 4th dimensional tensor, and each of those 4th dimensional tensors, there are 3D tensors, or you can think of it as 3D matrices, and then within those 2D matrices, and then vectors, and then of course scalars to the very end. Okay. So we can actually start indexing them when we think about this part. So we'll start with the easy one, so like a vector. So a vector you can kind of think of as more like a list. So all the normal properties that you would think of for slicing and dicing a list, you can see it right here. So we have our vector that we started up. Oh, let me put it back into it. It's a little easier to read without this reshaping. We can see right here is that our vector, basically we can get from the second element, number 1, right, to 4, which I think there's only 4 elements. So it goes 1, 2, 3, right? If we have every other element, you guys have seen this before, is that, have you guys seen this notation with the double colon in 2?
Not really.
Not really? Okay, so this is actually a little shortcut, what's going on here. So you guys probably know, for example, I go from 0 to, I think this is a length 4, right? Is that right? Yeah, there's length 4. So if I go from 0 to 4, right? You'll see it goes like all the way 0, 1, 2, 3. I can add an extra part here, this second colon after, and that tells you how to count and say, oh, I won't go to 0 to 4, but I want to count every other one. So instead of going 0, 1, 2, 3, you'll see it goes instead 0, 2. So starting with the beginning, 0, every other one, count by 2 essentially. But since we know 0 to 4, it's like, oh, well, that's just getting the whole list. We could have also run 0 to 4 just like this, right? That just means get the whole vector, right? So if I do another colon, it says get the whole vector. Another colon says, all right, how should I count? That 2 part means, oh, count by 2. So it's just kind of like a shortcut going through here. But I could have also done, for example, 1, 2, 4 like this. So now my elements would only include 1, 2, and 3. So what I'd expect then is counting from 2, starting with 1, was 1, skip over 2, 3. So we'll see 1, 3, like that. Okay. And so again, getting the whole vector, we just kind of talked about that. You can see how this one that's kind of fun is that you can do negative numbers to count backwards. So essentially it's like, okay, get the whole array or the whole vector, okay? And then instead of count by 1s, but count from 1s backwards. So you can actually reverse this vector direction. So, and then anyone got an idea what -2 would give like this?
The second from last. Every other one starting from the last one.
Yeah, so every other one starting from the last one. Actually, I think we should make a little subtle point. If I start from 1 here, you'll see that it'll start from 1, but counting backwards like that. So it's going from this direction, then going backwards. So play around with that a little bit, but just kind of know that's what those numbers are doing. Okay, cool. All right, so that's a vector. So vectors are pretty simple because I think we have lists. And we understand what a list is. Okay, matrices starts getting a little complicated, especially in NumPy notation. Now, the nice thing is that if you're using .iloc from Pandas, this actually has the same notation. And that's because, again, Pandas is built on top of NumPy. So it uses a lot of that terminology, that same kind of structure. So we have element at the first, So this one right here is just getting just one element. And we're getting an element from the first row, first column. I really should just comment these parts out so you can see it better. So you can see if I have, I should probably print out our whole matrix so we can check that out. Sorry, guys. So if we see our full matrix M, we can see it goes from 0 all the way through 7 for each of those parts. So we're getting basically the first row, our first vector, right? And then the first column, our first element within that vector, 0, 0, okay? If we're doing the next part, we can actually see, what's it, -1, -1. So what element should we expect to see?
7.
7, right? So It gets that very last element. Cool, right? Now this next one's a little trickier where we actually say, all right, get the first row, and then this colon right here, what did this colon mean before? When we had just like an empty colon?
Everything to the end of the list?
Everything, right? So it's getting that first row and then get everything in that row. So we would expect in this case a vector 0, 1. Okay, basically it's getting the first row and get everything. This one's a little different right here. Is we're getting, oops, sorry guys, messing up my, okay. So we're getting the matrix, right? We're getting all the rows, but only the first element in those rows or in those vectors. So we're getting all vectors, but in this case, we are only getting the first element in each one of them. So we'll actually see now, when we print this out, we'll see essentially like a vector that is printed outward like this. See that? So you can see that 0, 2, 4, 6 is this 0, this 2, this 4, this 6. Okay. And then obviously we can just print out the whole matrix, and that just gives us the same thing as M. Right? So you notice if I just do this part, it gives M. Anyone got an idea if I just put the number 1 in here, what that would print out?
The first
Would you print out
row.
only the 0, 1?
Only 0, 1? Okay. That's the nice thing is we can check it out, right? So you can actually see it prints out 2, 3. I think you had the right idea,
Oh,
Matt.
sorry.
Yeah, we count from 0. So yeah, but you had the right idea. It's like we're only printing out this part. What if I did just 1, 2, 3 like this? What would that print out?
2, 3, 4,
Everything
5.
but 0, 1.
Everything but 0, 1. So we got this one, and then Assad, you said something?
I was saying it wouldn't print the last one, would it? 0, 1.
So again, let's check it out, right?
Oh yeah, no, you're right.
No, you're right, Assad. So remember, it doesn't count that last index right there.
Oh yeah,
So,
because
if
it's okay,
yeah, it's okay, Matt. I see you. Yeah, you'll get used to this too. So you can see it prints out basically row 1, we start from 0, and then row 2, and then don't include row 3. So you can see right here, it's like, okay, this part includes. The reason, I think part of the reason why you can do this too, is if you do like print, like if you imagine doing like print of x from 1 to the length of x, that way you can get the last element every single time. So I think that's where it comes from. I could be wrong, but that's what I kind of think of. But anyway, so you can see if I just pass just one part without that comma in there, we will get just basically portions, those vectors. Okay. So, but if we wanted to include those those elements within the vector, we can do this part. Okay. So this brings us to the next part, which is just different parts of a tensor, which can obviously get a lot more complicated because now we have not just two, we don't have just 2 elements or 2 dimensions we can cut across. We can now cut across 3. So I kind of throw these parts out, and I should actually show what a tensor is. So remember we made this earlier, but to refresh our memories to say what this tensor is, that's our full tensor. Okay, and remember it's we can actually do the dot shape too. I'll do that later. But basically, you can say that there's 4 matrices, and each matrix has 2 vectors, and each vector has 3 elements. Okay, so if we do this part right here, if we get just 0 from this part, this will give us just the first matrix, right? If we have 0, 0, it'll get us the first matrix, but of the first matrix's first vector. So it'll give us just this guy right here. And then if we have 0, 0, 0, okay, we actually get the first matrix's first vector's first element. Okay, so we can see now, kind of break that down. We get at first that first matrix, and then we get just that first vector of the first matrix, and then we get the first element of the first vector of the first matrix. Okay, mouthful, but you can do it, right? And so this kind of breaks it down a little bit. It's like, okay, this right here will give us a 1D because we're getting the first matrix, we're getting just the vector, the first vector, but we're getting all the elements. So we can actually see that this will be a one-dimensional part, right? It's just a vector. Okay. Same thing would happen if I did like 1 to, in this case, 3. right? Or just to say from the first one to the end, we'll just see the same thing, but gives us just 1, 2. Okay. Note, however, this is kind of fun. If I do this part right here, we actually will only get one element, and you can see essentially we can think of this either a scalar or we can say it's a one-dimensional vector with one value in it, depending on what your interpretation is of how you want to describe that. Okay. I think most people would call this a vector, but you could potentially treat it like a scalar because we are just getting one element. Again, like if you go like this. See, so it depends how you want to interpret that. You have to be careful. Okay, but the idea is that if we can get a 1D matrix and stuff, or 1D vector. Okay, I guess all vectors are 1D, but whatever. Okay, so then right here we have interpreting through. So I'm going to try to kind of read this out, and the way I kind of said, like, what are we getting? What's the first thing we're getting?
It's getting the first matrix,
Okay, first matrix.
all of the elements of the matrix.
Okay, all the elements of the matrix, which are what kind of things are inside the matrix?
Which are 0, 1, 2, 3, 4, 5. It's the two vectors.
Good. So yeah, so each element is a vector. Good.
Yeah. Yeah.
Okay.
And all the elements of the first vector.
Yes, we're getting the first element of this. So good. So this is kind of complicated, but you can kind of look at this like, all right, we're getting the first matrix. And then of those matrices, we're looking at of that matrix, we're looking at just the first, or all the vectors. And then of all those vectors, we're getting just the first element. So you can see here, we actually get 0 and 3. And you can see we actually get those as a vector. You're essentially getting just this column right here. Okay. And this one's a little more complicated now. So I'll kind of walk this through. We have our first matrix. We're getting all the vectors. And then we're getting all the elements after the first one. Okay, so that means basically we go take this guy again. We're getting all the vectors, 0, 1, 2, and 3, 4, 5. But in this case, we're ignoring the first one. We're starting at 1, element 1 onwards. We get 1, 2, 4, 5. And you'll actually see instead of having a one-dimensional thing, oh, no, I'm sorry. We'll have a two-dimensional. I don't know why I put 2D, 1D here. But you'll have a two-dimensional matrix. Okay? All right. So we can also do other things like just kind of show you. I can get multiple matrices, and this will end up being a 3D tensor again. So you can do slicing and dicing. This stuff, I think, to be honest, can take some time to get your head wrapped around a little bit. But I think the best way to think of it is saying you're taking that next lower dimensional tensor object and then moving down, 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 down. Okay, cool. Any questions on this? All right, awesome. So then it brings us into some basic properties. So this is, I kind of alluded to this, is our shape. So you'll notice that when I did the very, very beginning, I did, where is it? All right, reshape, okay? So this kind of gives you the idea that there is something called a shape, right? We can actually use shape right here, right? So in this case, we have a scalar. I'm sorry. Why did I put a scalar here? Okay, sorry. It's not a scalar. I don't know why. NP array. Sorry, I'm like rereading my own thing and I realize. Oh, I'm sorry. Okay. I was reading this as a range. This is not a range. This is an array. So I made an array and that's the element is just 100. So you see when I print out S, it's just 100. The shape, you'll see here, there's nothing in it because it says 0 dimension. I see how it's coming all together. And we can see this dot size. This is these shape and size are properties that belong to this array, which happens to be scalar. And the size is just 1. There's only one element in it. Okay. Then we have our vector v. So we print this out now. We can see what our vector v looks like. 0, 1, 2, 3. Right. That's our vector. We can see our shape now is 4, comma, nothing. Right. There's a one-dimensional shape, one-dimensional object. Its shape is basically there's 4 elements in there, okay? But then there's nothing after that. And the size is just 4, okay? So our matrix now, and maybe I'll give you guys a little quiz, right? If I'm printing out this matrix right here, is anyone got to guess what the shape will be?
4, 2.
4, 2, okay, so let's check it out. Thank you, Hassan. And we got it, 4, 2, right? Cool. And then obviously what's the size is just how many elements there are going to be. I think you guys kind of have that figured out. And so you can see there'll be 8 elements. And so an easy way to find the size, like kind of makes sense, is that if you do 4 times 2, basically the shape in here, you'll find out that's how many elements there are. Okay. And that's why I could actually do that when I did a range where I had like 8 elements, I did 4 times 2 elements, but then reshape it as a 4, 2. That's why I can get that part. And then 3D tensor, we can actually see really quickly what this 3D tensor is. We can see what the size is, and we can see the size is the 24, okay? And so that kind of gives you a clue that the shape's gonna be 4 matrices, 2 vectors, and then 3 elements in each one. So we'd see 4, 2, 3. Okay, not too bad. If I had a bigger matrix, this obviously can keep going on and on and on and on. And you will see those kind of shapes and stuff like that sometimes because your tensors can be very large, depending on what kind of data set you're looking at. Okay, so that's quick thing. This is very useful, the shape and the size, to see like what your thing is. And then, because this can be kind of hard to like parse, like especially if it's very large tensors, they can be very difficult to figure out what they are. So this gives us a quick idea of what kind of shape it is. And this will be important when we actually start doing the math on top of the for linear algebra. But we have something also called transpose, which of course I got rid of. But basically, I think of this, it's not the best way to think of it. I think of like you turn your matrix on its side. So for example, we have our original matrix M, and I can do M dot T. So let's see here, yeah. So I also write M dot T, which is the shortcut of doing the transpose. You can also do NP dot transpose, that function, and apply it on M. But you'll see me usually use this just because it's a lot quicker to write. But you'll see we have our original matrix right here, right? And you see it's 4 rows, 2 columns, 4 vectors, 2 elements in each one of them. And I do a transpose, you can see the shape actually essentially reverses. And you can see that now we have 2 vectors, but each with 4 elements. And you can see the vectors, you can kind of see where this comes from. This part right here, this part right here. When we do a transpose on a higher dimensional set, you can think of like you're doing a transpose within the different elements. So I'm not gonna hang on this too long, but you can kind of play around with it. So we have a 4, 2, 3. So when we transpose that 3D tensor, we get 3, 2, 4. And you can kind of see really quickly that, was it 0, 1, 2? You can see it's a little harder to see, but you can think of like you transpose the different elements within here. I won't go into full detail about that because that's, to be honest, it's just a lot of like mental work to get around it and stuff like that. But note that sometimes we'll have to transpose shapes when we're multiplying them together, just because of the nature of how they work. And just something to be useful to know.